Hi, this is part 5 of chapter 5. So, in this part, we are going to talk about covalent bonding and molecules. All right. So, before I start this topic, I wanted to remind what we just discussed just before I talked about ionic compounds. In this chapter, previous two sections, we discussed about ionic bonding and how to name ionic molecules. And in this section, part 5 and part 6, we are going to discuss about covalent bonding and how to name covalent molecules. So when I start discussing about ionic compounds and how to name ionic compounds, I specifically ask you to use those rules particularly for just those ionic compounds and do not apply those rules anywhere is because covalent compounds and covalent molecules names looks different than what we just discussed for ionic compounds. Now, the way ionic compounds forms bonds is different than the way covalent compounds forms molecules. So they were just two different types of compounds. So I want you to compartmentalize what you learn about ionic compounds and how to name ionic compounds separately, and compartmentalize these covalent bonding and covalent molecules separately because they were not alike. Again, please do not confuse one with another. We are not going to discuss the ionic compound naming rules in this section. We are not going to follow what we just discussed about ionic bonding in this section because covalent bonding is a different type of bonding compared to ionic bonding, and covalent molecules are named differently compared to ionic molecules. So please have that compartmentalization. Now let's dig into what is covalent bonding and what are covalent molecules, right? So covalent molecules comes into mind when you have a bond between two nonmetals. Okay, that's the simplest thing you need to know. But why? Why two nonmetals results in a covalent bonding? So covalent bonding, in other words, is a shared bond. It is called a shared bond because two elements share electrons between them instead of one giving it to another to form ions. It is not happening. If one giving the electrons to another, we call them as ionic bonds. But the covalent bond is called a shared bond. In other words, shared bond is because elements are sharing electrons between them. So they were cooperating between them to share the electrons. Why are they sharing electrons between them? Because they have similar chemical properties. No element has a huge electronegativity difference one to another. We remember in chapter 4 we discussed the electronegativity. All the non-metals has comparably similar electronegativities in comparison to metals versus non-metals. Metals versus non-metals has huge electronegativity difference. So, they form ions by one giving electrons, one taking electrons. But here, all non-metals has comparable electronegativity value. So no one is able to take completely electrons away from another element. So here, the only option they have is to make themselves stable to achieve the noble gas electronic configuration is by sharing electrons. So whenever you see two nonmetals together, think of them as they were sharing electrons, not giving away electrons to another, just sharing electrons to form a covalent bond, a shared covalent bond. Why do they do that? Is to achieve the noble gas electronic configuration. If they share electrons, each element can feel more electron cloud near them, which resembles the noble gas electronic configuration if they fill up the electrons they're supposed to fill up. Okay, we're going to spend entire this part and next part on this topic. So if I don't make sense yet, just hold on to it. Okay, in a few minutes it will make sense. All right. So what we just discussed is it is all based on Lewis theory of bonding. We just discussed about who is Gilbert Lewis is. He proposed the Lewis dot symbols and valence bond theory, which we are going to discuss in next two chapters. So he proposed how elements make bonds with another elements. So according to his theory, two nonmetals, whenever they make a bond, They make a bond by sharing electrons between them. What does it look like when we say sharing electrons between them is, let's look at this simple example. So in the simple example of molecule H2, say that two hydrogen atoms are sharing electrons right here. How it is happening, let's discuss that. So first, let's see what are the valence electrons present for each hydrogen element. Each hydrogen element has one single electron, okay? So when they have this one single electron, currently, they don't resemble any noble gas electronic configuration. The closest noble gas electronic configuration helium can achieve is helium, 2 electrons. But each hydrogen currently has only just one electron. So how can it achieve the noble gas electronic configuration is if they both share electrons between them. So they give its electron to another, so another element give its electrons to opposite hydrogen. So eventually they share these two electrons between them. So we call this one as a shared bond. So as a result of them sharing electrons between them, now they were connected to each other. So they form a molecule. So individual hydrogen elements now are part of a molecule because each one has one electron, they shared with another, now they just form the molecule. And now they were connected to each other forever until something break them. So the way these two are connected is by sharing electrons. So this sharing of electrons we call in chemistry as a covalent bonding. The sharing of electrons results in covalent bonding. So when you have a covalent bonding observed between molecules, you call that bond as a covalent bond. So whenever you hear a term covalent bond from now on, you need to imagine that, oh, those elements shared electrons. They must be nonmetals because only nonmetals can share electrons between them to form a covalent bond. Okay, now that we introduce what is a covalent bond is, let's pound on it and learn more about it, then eventually learn about how to how to find the bonds between them, how to identify chemical formula for a covalent molecule. All right. So a molecule, when we say molecule, we can easily say that we are referring to a covalent molecules. We kind of result the word molecule for covalent molecules, and for ionic compounds we use the word formula unit. So when we say casually molecules, we are trying to say covalent molecules from now on. The covalent molecule is a combination of at least two atoms or more in a specific arrangement held together by chemical forces, which are nothing but our very own covalent bonds. Okay. A molecule may be an element or compound. What does that mean? There are some elements that exist in the form of diatomic elements. Most popularly, you can tell oxygen, the oxygen gas that we inhale every day exists as a molecule, not a single oxygen. It is stable as O2, and so is nitrogen. So they were stable as diatomic molecules. Those are just two examples. Or a compound molecule can be a compound. What is the example of compound? Water, obviously, right? More than one different element is making covalent bonds between them, so it is a molecule. Now, how do I know these chemical formulas? How do we know how they will exist? So for this, we are going to talk about a couple laws. There are two laws that I want to specifically introduce. And whoever taking any, let's say, competitive test, one of these laws will always going to be tested in the competitive test, for example, MCAT or DAT or any other test that is competitive after general chemistry. So this is kind of basic information expected out of a student to know what is, law of definite proportion is. Kind of like, common sense in chemistry. So that's why, they always ask, I guess, just to check if the student has common sense or not. Okay. So what is law of definite proportion is that when two of the same compounds, when two of the same elements connected with each other through a covalent bond in a same ratio, no matter what sample you collected from, where you collect from, they should always be in a similar ratio found in the molecule formula. So what does it mean is, let's look at the carbon dioxide as an example here. Carbon dioxide, no matter where you collect that sample from, if you try to identify the amount of oxygen and carbon present in the collected sample you have and try to identify the ratio it present at the end, it should always end up the same if you still collect the pure carbon dioxide. Let's say you take 123 grams of carbon dioxide and identify the mass of oxygen as about 89 grams and mass of carbon about 34 grams. You end up with ratio of oxygen to carbon as 2.66 to 1. Let's say you took 50 gram sample and identify mass of oxygens and carbon, your ratio is still the same. That's what law of definite proportion is. As long as you have the same elements that are connected to each other in the same ratio, no matter where you collect the sample from and how much of a sample you have, you should always have the same similar ratio. Again, about 90 grams of carbon dioxide, that results in the similar ratio of 2.66 oxygens to just 1 carbon, right? So you know one law, which is law of definite proportion. Here is another example here. Carbon monoxide. Now 16 grams of carbon monoxide and 26 grams of carbon monoxide, 88 grams of carbon monoxide. Different samples, right? But if you try to identify the masses of oxygen and carbon in both of them, and if you try to identify the ratio for oxygen to carbon, you happen to have same ratio, because according to law of definite proportion, you should have the similar ratio. It doesn't matter what mass you started with, because at the end you have just one compound. So why the ratio should change, right? So that's what law of definite proportion is. Now let's talk about law of multiple proportion. So what law of multiple proportion says is that if two elements can form two different compounds, like this carbon and oxygen forming carbon monoxide and carbon dioxide. In one you have 1:1 ratio, in another you have 1:2 ratio. So according to law of multiple proportions, if two elements can form two different compounds, okay, law of multiple proportions tells us that ratio of the masses of one element that combines with the fixed masses of other element can be expressed in a small number whole ratios. Okay, so now what you have is fractional ratios of 1.33 versus 1 carbon, 2.66 oxygens versus 1 carbon. They were fractions, right? 1.33 is a fraction, 1.66, 2.66 is a fraction. So using the law of multiple proportions, we are going to come up with the whole number ratio so that it is easy to communicate. Wouldn't it be easy to write to CO2 instead of CO 2.66? Wouldn't it be easier to write CO instead of C1 and O 1.33? It's very hard to remember, right? So that's why using the law of multiple proportions, we are going to come up with the whole number ratio for this carbon oxygen and carbon oxygen CO2. We are going to explain where those CO and CO2 come from. So these are the ratios currently for carbon dioxide and carbon monoxide respectively. Now, using those two, we are going to identify what is the ideal ratio of the whole number oxygens should be for both in carbon dioxide and carbon monoxide. Because carbon ratio is 1, the common denominator. In carbon dioxide, you have 2:1, 2 oxygens to 1 carbon. In carbon monoxide, you have 1 oxygen to 1 carbon. So we are going to cancel 1 and 1, which is going to end up with just 2/1. So which means in carbon dioxide, you should have 2 oxygens. In carbon monoxide, you should have 1 oxygen as your whole number. You can also do that from here, the ratios of one over another, that giving 2:1 ratio. So that is how we have these whole number ratios instead of having the fractionals, even though it's not directly related to actual mass ratio. Okay. All right. Now that we know how law of multiple proportion and law of definite proportions works, let's focus on how to familiarize with the different types of covalent molecules. Covalent molecules can be largely grouped as diatomic molecule, just like the name suggests. It contains just two atoms. Okay. Or you can say like heteronuclear diatomic molecule or homonuclear diatomic molecules. Hetero means two different. So in those diatomic molecules, you have two different atoms. In homonuclear diatomic molecules, you have a diatomic molecule, but both of them are same element. And other ones are polyatomic molecules, which means you have multiple elements combined together, more than two. So just like name suggests, very easy to predict what's going on. Here, some of the popular color symbols that we use to represent, some of the popular non-metals we hear, or maybe these are all non-metals that we have here. Sometimes, until you guys get really familiarized, we use these color codes. And also, if you're using elemental bond models, we use the bond models to make molecules, hands-on molecules, and most of them follows the similar color pattern. So just know that different color is assigned differently so that we can easily communicate or differentiate one from another. Okay. So let's spend some more time on familiarizing ourselves with molecules. We already know that molecules are formed as a result of nonmetals sharing electrons between them to form a covalent bond. And if two or more nonmetals share the electrons between them through covalent bond, we call them as molecules. Okay? And molecules are represented with a chemical formula. And a chemical formula denotes the composition of the substance. What it means is it tells how many of the atoms there are. There are two hydrogens and one oxygen. That's the chemical formula of water. Molecular formula, which is same as chemical formula, right? There are just two different ways of saying it. Shows the exact number of atoms each element in a molecule, same as H2O. You have two hydrogens and one oxygen, same as one oxygen and two hydrogen. These are all different ways of expressing chemical formula or molecular formula. Other types of molecular formulas, some of them are grouped as allotropes. Allotropes is a word specifically used when you have a single element exist in more than one molecular formula. Those are called allotropes. Here we are discussing the example of oxygen allotropes, where oxygen exists as O2 gas that we inhale, and ozone, O3, that is used as protective layer for our troposphere, Earth, to protect us from radiation. But both of them are oxygen molecules, but they have different number of atoms in them. So the relationship between oxygen, O2, and ozone, O3, they were allotropes of oxygen molecule or element. So sometimes you see the word structural formula. Structural formula is more detailed way of showing the chemical formula. It clearly shows which element is connected to which element. So water is showing that oxygen is connected to two hydrogens through a bond like this. And there are just two different ways of showing the structural formula. All right, we don't have animation for this. You can already see the solution. All right, that's fine. It's very simple problem. Let's look at the problem and discuss. Write the molecular formula of ethanol based on its ball and stick model shown here. So remember 2 slides ago, I showed different colored elements. So here, black is popularly used for carbon, and white is popularly used for hydrogen, and red is for oxygen. Okay. So it is just asking you to write the molecular formula based on the given balanced model. It is called balanced model. So here you can see 2 carbons and 6 hydrogens if you count. 1, 2, 3, 4, 5, and 6, and 1 oxygen. So there are 2 carbons. So your chemical formula or molecular formula is going to be C2H6O. That's how you would identify. Very simple. Now and then you would come across this new word, maybe in here and maybe in organic chemistry class if you take it one in future. Empirical formulas are easier way of communicating the what is the ratio of 2 or more elements connected to each other. What is the simplest ratio they exist in? You can have same elements exist in many different ratios connected to each other, like you have carbon monoxide and carbon dioxide, right? Just like that. So if at all possible, you want to express them in the smallest ratio they connected to each other so that we can easily understand what is the nature of that molecule is by seeing the which one is dominating. Is it oxygen or is it carbon? Is it hydrogen? So that practice is called the empirical formula, because instead of truly giving the formula, like truly giving the what's the exact ratio, exact number of each element is present, it just tells the what is the simplest ratio that is present, because it makes more sense when I show you an example. So here you have a molecular formula of N2H4. In N2H4, you have 2 nitrogens and 4 hydrogens, okay? But can you express it simply without changing much? Obviously, you can. If you try to find the common smallest ratio, that is, if you divide both of them with the 2, you would find that it has NH2. What it means is for every 1 nitrogen, you have 2 hydrogens. So more hydrogen atoms for single nitrogen. So that's the way of trying to express the empirical formula. It looks unnecessary for the simple problem like N2H4 to NH2, but for the more complex molecules, that is highly useful in some cases, knowing the empirical formula. So we're just going to go over a few examples of empirical formula and molecular formula, molecular model. For water molecular formula is H2O. And its empirical formula, you cannot make it any more simple because you already have one element, just one ratio. So you cannot make that any more simple. So its empirical formula and molecular formula is same. But hydrogen peroxide has 2 hydrogens and 2 oxygens, so which you can make it simple by OH. It's the ratio. 1 oxygen is to 1 hydrogen. Ethane, C2H6, you have at least 2 carbons and even number of hydrogens. So obviously you can make it to smaller by saying for each 1 carbon there are 3 hydrogens. That's the empirical formula of ethane. And a propane has C3H8. Whenever you have odd numbers, it gets tricky. So 3 carbons and 8 hydrogens. You cannot make it any more smaller by dividing with the 3 or 2 or 1, right? 1 is useless anyway to get this smallest empirical formula. So its molecular formula is same as empirical formula. And acetylene is C2H2 and it is now CH. Benzene is C6H6, it is now CH. Now, let's apply what we just learned. So the question is asking us to write the empirical formula for the following molecules. For glucose, it has the chemical formula of C6H12O6, and for the adenine, C5H5N5, and for nitrous oxide, N2O. Let's work on it. For glucose, let's see if I can show you the strategy. I want you to work on it before you look at it. It's a very simple concept. For glucose, I see all even numbers. for 6, 12, and 6, which means I can find some common denominator to cut down the ratio to smallest possible. So if I divide all of them with 6, I should get the smallest ratio of carbon to hydrogen to oxygen. If I do that, I will have CH2O, which is fantastic. That is the smallest ratio of carbon to hydrogen to oxygen that I can find. I cannot divide them with the 2 or 3 or 4 because that is going to give them either fractions or still bigger amount of carbons. So if I divide them with 2, for example, as we discussed here, I would end up with the 3 carbons. But having 1 carbon is better than 3 carbons. But if I divide them with 3, I'll end up with still 2 carbons. But having only 1 carbon is better than 2 carbons to get the simplest formula. What about adenine, C5H5N5? Looks as easy as it can get, right? Each one of them has same number of atoms, so 5, just divide all of them with 5, you would end up with CHN as your empirical formula. See, it gets easy. And for C, the nitrous oxide, I call laughing gas. I'm not laughing. Yes, I am. I'm not even inhaling nitrous oxide, but still I'm laughing. So how do you find the smallest ratio for N2O? How about you divide them with the 2? You divide them with 2, you have 1 nitrogen but half oxygen, but that doesn't work. You need to have the smallest whole number ratio. So which means you cannot have any more smaller empirical formula than its molecular formula. So whatever you're looking at, N2O is its empirical formula. That's all for this part. I'll see you again in the next part of this chapter.